In section 13.4, we look at how we can use equilibrium constants to calculate the amounts of reactants and products that will be present in a system that is at equilibrium. In complex equilibrium problems, often concentrations of some species may not be known. When we're trying to determine what these concentrations are, a good place to begin is by setting up what's called the reaction table, which many people call an ice table. In the reaction table, what we'll do is we'll write on the top line the units that we'll be working in, which will either be ATM or molarity, depending on whether we have a Kp or a Kc, our reaction, and then underneath our units, we're going to put the letters I, C, E to indicate initial changes in concentration and equilibrium concentrations. And then we will insert the information that is available to us into these rows. So here's an example. It says solid graphite that has been heated to 1080 Kelvin is reacted with carbon dioxide at an initial pressure of 0.458 atm, and then we are given the reaction. It says the system is allowed to come to equilibrium, at which time the total pressure is 0.757 atm. What is Kp? So what is the equilibrium constant in terms of pressures? So I'm going to set up the ice table and put in the information that I know. Now they're asking for Kp, so I need to work in atm. And then in my top row, I'm going to finish that off by putting in my equation. Now I note that one of my reactants is a solid, so I don't need to worry about the concentration of that species in my ice table. My other two reactants are gases, however. Initially, I have 0.458 atm of my reactant. Now, there is no note of any product being present, so the initial concentration of the product must be 0. The system is going to move into equilibrium. It must move towards the right-hand side because there are no products to convert into reactants. So the system is going to make some products by shifting to the right. That means that the CO2 will go down by some amount x, and the CO will go up by some amount 2x. I know this because for every 1 CO2 that is consumed, 2 COs are produced. So when the system comes to equilibrium, I will have 0.458 minus x atm of CO2, and I will have 2x atm of CO. Now, back up in the problem, they said the total pressure is 0.757 atm. So that means that if I add together the pressure of the CO2 and the CO, I'm going to get a value of 0.757. So knowing this, that means that I can now solve for what x is. So working through the math, I determined that x is 0.299. So now I can insert x into my ice table and update for the new values. And there we are. So here's my bottom line of my ice table. Now the problem asked us to calculate Kp. So Kp is going to be the concentration, or in this case, the pressure of the CO squared divided by the pressure of the CO2. We don't need to worry about the solid carbon. So this is going to be 0.598 squared over 0.159, and that gives me a value of 2.25. So that's how we might use the ice table to determine a K. Another kind of problem that we'll often see is that we're given the equilibrium constant and we're given the starting amounts of reactants, and we're asked to determine the equilibrium concentrations of our reactants and products. So let's have a look at an example like that. It says for the reaction shown below, at 900 K, Kc equals 1.56. It says if carbon monoxide and water are combined in the same vessel to give initial concentrations of 2 mole per liter and 1 mole per liter respectively, what are the equilibrium concentrations of carbon monoxide and water? So what we're going to do is we're going to set up the ICE table and we're going to put in the information that we know. So this time we're working in molarity because we have a Kc and we were given some concentrations in molarity. So we've got initial change equilibrium in our first column, and we have our units and our reaction across the first row. In this case, there are no terms that we're going to be omitting because everything is a gas and there are no solids or liquids present. To begin with, I have just reactants. I have 2 moles per liter of CO and I have 1 mole per liter of H2O. I have no CO2 and no H2. So that means that the system must move towards products because it's unable to move towards the left-hand side. So my reactants are each going to go down by some amount X, and my products are each going to go up by some amount X. And the reason that this happens is because we have 1 mole of each of our reactants and products. So whatever one thing changes by, the other thing changes by an equal amount. When the system comes to equilibrium, I will have 2 minus X moles per liter CO, 1 minus X moles per liter of H2O, and X moles per liter of both CO2 and H2. So, writing out the expression for K, we have products over reactants, and everything is raised to the power of 1 in this case. We can now start substituting in our equilibrium values. So CO2 has an equilibrium value of X. H2 also has an equilibrium value of X. So my top line is going to be X squared. Carbon monoxide has an equilibrium value of 2 minus X, and water has an equilibrium value of 1 minus X. So I'm just going to kind of like distribute everything in the bottom line and collect like terms, and I end up with this. So X squared over X squared minus 3X plus 2 equals K, which in this case is 1.56. So what I'm going to do now is I'm going to bring everything to the one side, and I'm going to collect like terms. And so I'm going to work through that algebra here, and I end up with this expression. So 0.56x squared minus 0.468x plus 3.12 equals 0. And you can probably recognize that this is a quadratic equation. It has the form ax squared plus bx plus c equals 0. And we can solve for x by using the quadratic formula. So, just recapping in case you forgot, a quadratic equation has the form ax squared plus bx plus c equals 0. And in our equation, we have 0.56x squared minus 4.68x plus 3.12 equals 0. So this means that A equals 0.56, B equals negative 4.68, and C equals 3.12. So now we're going to use the quadratic equation to solve, or the quadratic formula, to solve for x. So x is equal to minus b plus or minus the square root of b squared minus 4ac on 2a. So it takes a little bit of while to grind through this, but eventually we decide that X is either equal to 7.6 moles per litre or 0.73 moles per litre. So what one is it? Well, if we look at our data up here, we realize that the value of X must be smaller than 1, because any bigger than 1 and our equilibrium term for the concentration of water would become negative, and there's no such thing as a negative concentration. So, considering our reaction table, we realize that the only value of X that makes logical sense is 0.73 moles per litre. So now we have our value of X, we can go ahead and update our ice table for the equilibrium values. And that's what we've done here. You just put X in and evaluated each of our terms there. So now we've calculated the concentration of all reactants and products when our system comes to equilibrium. So in that particular example, we had no products present. So we knew that the system was going to shift towards products. However, sometimes we need to calculate Q first so we know what direction the change will occur. So I'll do an example of that now. So it says in this problem that the value of Kc for this reaction, which is N2O4 decomposing to form 2NO2, is 0.21 at 373 K. And what's different about this is that we're told that our reaction vessel initially contains 0.03 moles per litre NO2, and it also contains 0.03 moles per litre N2O4. So now we're asked, what are the concentrations of both of the gases when it comes to equilibrium? So in this case, both of our concentrations are non-zero, so we don't know what way it's going to move. So let's set up the ice table and then we'll calculate Q to see what way the system is going to shift. So here's our ice table. We have a Kc and we have molarity, so we're going to be working in moles per litre. This is our reaction, N2O4 becomes 2NO2s, and our initial concentration of each of our components is 0.03 moles per litre. Now, we don't know what way it's going to shift until we calculate Q. So Q is going to be products over reactants, but we have to square our products because we have two of them. So that means that Q is going to be equal to 0.03, which is less than our value of K. So as Q is less than K, that means that our system will shift towards products. So that tells us what way things are going to move. So what that means is our N2O4 will go down by some amount X, and then our NO2 is going to go up by 2X. So when the system comes to equilibrium, the concentration of N2O4 will be 0.03 minus X, and the concentration of NO2 will be 0.03 plus 2X. We can note at this point in time that X must be less than or equal to 0.03. If X is any bigger than 0.03, the concentration of N2O4 would become negative, and that's not possible. So we proceed similarly as we did before. Kc is equal to our concentration of NO2 squared divided by the concentration of N2O4, which is equal to 0.21. So we're going to bring everything to the one side, distribute everything, collect like terms, and ultimately we end up with a quadratic equation. We're going to put our numbers from our quadratic into the quadratic formula and solve for our two values of X. And we get two values, one is negative and 1 is positive. Now, negative values for X are not possible. So concentrations and moles can never be negative amounts. So we can immediately discount that guy. And this must be our value of X. So there we are. X must be 0.016. So now we can go ahead and update our ice table. So updating our ice table, we put 0.016 in for X. This is going to be 2 times 0.016, and we can get our equilibrium values here. So a little bit more complicated in this case because we had to calculate Q in order to know the direction that the system was changing. Okay, so that concludes the section on equilibrium calculations. But the take-home idea here is that if we are given initial concentrations and an equilibrium constant, we can set up an ice table, and that will help us determine the equilibrium concentrations of all of our reactants and products.